So, hello and welcome to this lesson. So, this happens to be the first lesson in our study of Mathematical Biology 2. So, I am Boydu Okran Rindolph, a final year student of Mathematics, KNUST, and I'll be taking you through this lesson. So, in our first series of videos, we'll be talking about models for single population growth or single species population dynamics model for them. Okay, so we'll talk about Malthusian model, the Verhulst logistic model, delay models, and harvesting in population models. Okay, so in this first video, we'll be talking about the first one, which is the Malthusian model. So the Malthusian model was developed by Thomas Malthus, okay, in the year 1798. So Malthus was an English mathematician. There are several factors which affect population growth. You can mention some of them yourself, right? So look around your environment and look at the factors which affect population growth. You can see that the first two that you can mention is birth rate, right? So when more people are born, that means that the population is going to grow. And we can also talk about death rate. When the number of people who die are more than those who are being born, then the population is going to decline. Then aside these two factors, we also have other factors which affect population growth, such as um, fire outbreak. When there is fire outbreak, people are going to die, right? Such as when there is starvation, right? When there is famine, we have a lot of them. Okay, but since birth rate and death rate are the main factors which affect population growth, Malthus only considered those two. Okay, so Malthus only considered birth rate and death rates. So how do we derive the Malthusian growth model? Alright, so we are going to look at a simple way of deriving that. Okay, so we are going to let B be our death rate and birth rate. Sorry, so B is the birth rate. We are letting D be the death rate. They are letting P stand for the total population. Alright, so know that the variables here, you can use anything to denote your birth rate, your death rate, and your total population. Okay, the most important thing is that you are able to understand what you are doing, so that whether the variable is B, D, or P, you'll be able to derive it yourself. Okay, alright, so let's consider a scenario here. So let's say in 2000, the population of a town was 10. In 2001, it was 15. In 2002, 17. In 2003, 30. Alright, so you can see that there is growth in population from 2000 2001. There is also a growth from 2001 2002, and there is also a growth from 2002 to 2003. Okay, so to get the average number of change in our population size from 2000 to 2003, it will be given by the change in population size over what the change in time taken. Alright, and this will be equal to the difference in what the birth rate times the population minus the death rate times the population. For instance, if let's say the birth rate is 0.12 and the population is 1200, if we want to know the number of people who were born, it will be the birth rate times the population, which will be 0.12 times 1200. Okay, right? So the change in population size over change in time taken will be equal to the number of people who were born minus the number of people who died. That will be the change in what? The population. Okay. Alright. So I hope you understand this statement here. So we will consider change in the continuous sense, not in the discrete sense. Okay, so when you are considering change in the discrete sense, we use delta to represent our change, but in the continuous sense, we use d, derivative. So that means we can write this here as the change in population size as dp and the change in time as dt, and it will be equal to b times p minus d times p. But you consider we have a common variable here which is p, so we can factorize that out. And that will give us the pdt will be equal to b minus d times p, right? So you can see that this b and this d here are all numbers, and when you subtract two numbers you always get what? A number. So we are saying let k be equal to b minus d. So k will be equal to the difference between the birth rate and what? The death rate. Okay, so letting k be equal to b minus d, will have the p dt will be equal to k times p, and let's call this equation 1. So in equation 1, our k is what we call the intrinsic growth rate of population. Okay, and equation 1 is what we call the Malthusian growth model, which is also known as the exponential growth model. So we've been able to derive it. Okay, right? So if you didn't understand anything when we're deriving it, you can go over and you realize that it's not difficult at all. So now that we have our model, how do we analyze it? So let's talk about analysis of the model. So the population will grow if our k is greater than 0. And why do we say that? The k is the same as b minus d, right? So when k is greater than 0, it means b minus d is greater than 0, and this means b is greater than d. So k being greater than 0 means that the birth rate is greater than the death rate, and of course when the birth rate is greater than the death rate, that means the population will what? Will grow. And another thing we can deduce from the model is that the population declines when k is less than 0. So k is equal to b minus d. So when k is less than 0, it means b minus d is less than 0, and it means b is less than d. So that means that when the birth rate is less than the death rate, that means that the number of people who are dying are more than those who are being born. So of course the population is going to decline. I hope you get that. So we can make these two deductions from the model we had. So right now we have the model which is dp dt is equal to kp. Note that in some book you can see the n dt is equal to Rn. So for them, they use R to be B minus D, and they use N to be the total population size. Okay, and it is the same thing, just that we have different variables. Okay, so the solution of the Malthusian growth model. So we have the PDT is equal to K times P, right? So we can find the analytic solution to it using the method of separation of variables. So we have the PDT is equal to KP. Alright, so we can multiply through by the t. So when we do that, we have the t here, then the t here, but this dt will cancel this dt. So we have the p will be equal to kp dt. Alright, then we can divide through by p. So this p will cancel this p, and I will have 1 over p dp will be equal to kt. Okay, so when we get here, then we can integrate both sides. So when we integrate the right hand side, integrate 1 over p will give us ln p, and p is a function of time t, right? So we get ln pt, p of t. Then when we integrate k with respect to t, we get kt plus our c, which is the constant of integration, right? So this is the general solution. I want to find a particular solution, so that means that we have to get initial conditions and find c. So the initial condition is that at time t equals 0, p of 0 is equal to p naught, where p naught is the initial population, right? So making that substitution, we get ln p, but now t is 0, so p0 is equal to k times 0 plus c. Then p of 0 is equal to p naught, so you have ln p naught to be equal to c, since k times 0 is 0. So that means that c is just ln p naught, right? So we will take equation 3 and put it back into what? Equation 2. So wherever we see c, we put what? Ln p naught there. So doing that will give us ln p of t will be equal to kt plus ln p naught. And we can have ln p of t minus ln p naught is equal to kt. And you know, laws of logarithm, when you have ln a minus ln b, this is the same as ln a over what? B. So we can write this in this form, and it's equal to kt, right? We are finding for p of t, so we can find the exponential on both sides. And find the exponential on both sides, we'll get e ln p of t over p naught to be equal to e kt, right? And e ln p of t over p naught will simply give us p of t over what? P naught. So that's why you can see p of t over p naught is equal to ekt here. And you can multiply it by p naught and you get pt will be equal to p naught ekt. And this equation 4 happens to be the analytic solution for the model we had. And equation 4 is very, very important. It is used to estimate the population present at a particular time t when given the initial population p naught and the intrinsic growth rate, that's k. Okay, so this equation is very important. Don't worry, we'll be solving examples and you know why I'm saying is very important. So now let's learn how to linearize equation 4. So this is equation 4. How do we linearize it? Because sometimes we will have to do that in order to calculate one or two things. Okay, so we have p of t is equal to p naught akt. When we take the natural log on both sides, we get ln p2 will be equal to ln p naught ekt. And laws of logarithm, ln a b the same as ln a plus ln b. So we can write this here in this form. Then this will give us kt. Okay, we get ln p2 equals to ln p naught plus kt. So let's call this equation 5. So comparing this to the equation of a straight line, that's y equals mx plus c. What this means is that our k, right, is equal to m. So that means the k is the gradient of the graph, and our y is equal to ln pt, and our c is equal to ln p naught. So that means that the c, which is the y-intercept, is ln p naught. So p naught will be equal to just ec when we take the exponential on both sides. Okay, so this is how we linearize the equation 4. So right now, let's talk about interpretation of the equation 4 we had. So how you can use that to make some analysis based on the population. Okay, so we have pt is equal to p naught ekt, right? So from this, when we take the limit as t approaches infinity, that's if you allow time to grow like for a very long time, what will happen to the population? Okay, so when we take the limit as t approaches infinity on both sides, we'll get limit as t approaches infinity of pt will be equal to limit as t approaches infinity p naught ekt. Since p naught is a constant, it's a number, you can bring that one outside and we'll have this. So this k here, right, it's a parameter and it can assume some values. It can be less than 0 and it can be greater than what? 0. So we assume those two cases, and sometimes it can be 0. Okay, so when it is 0, it means that the population doesn't grow, so the population will be constant. So we don't mostly consider this case. We consider when it is less than 0 and when it is greater than 0. Okay, so case 1 is when it is greater than 0. So when k is greater than 0, this here will give us what? Infinity. So that means that the limit as t approaches infinity, p of t will be equal to p naught times infinity, and any number times infinity is infinity. So that means that the population will be unbounded, or the population will grow with no limits. Okay, so the interpretation of this case is that the population size will grow unboundedly as time becomes large. And consider the scenario when k is less than 0. We will have this being equal to 0, and p naught times 0 is what? 0. So what this means is that the population species dies out for a long period of time. I hope you get it. Okay. So now let's talk about the basic reproductive number, R naught. So if the birth rate B is greater than 0, then the average number of offspring or babies over the lifetime of an average individual over the Malthusian model would be B over D, where B is a birth rate and D is a death rate. So this ratio, B over D, is what we call the basic reproductive number, or R naught. So how do we interpret it? If our R naught is greater than 1, what this means is that the births exceed what? The deaths, right? And the average number of offspring per person over half lifetime is greater than 1. Or that is the population explodes, okay, because the ratio is B over D. So if this thing is greater than 1, it means that our population, our birth rate B is greater than what? D. So the population will grow, will explode. Then if R naught is less than 1, then deaths exceed births. The average number of offspring per person is less than 1, and the population dies out. I hope you get that. Alright. So that's the Malthusian model. So right now let's solve some examples on it and see how we use that to describe our population and to make some predictions. So the first question says that suppose the growth of a population is 0.7944 per member per day. Let the population have 2 members on day 0. Find the population size at the end of what? 5 days. And the second question says, suppose the population has 39 members at t equals 8 and 60 members at t equals 12. What was the population at t equals 0? So what's the initial population? So let's solve question 1. So question 1 says, suppose the growth of the population is 0.7944 per member per day. So this is our key. And let the initial population have 2 members. So this is our initial population. So you have to find the population at time t equals 5 days. Okay. So our k is 0.7944. Our p naught is 2. That's the initial population. And we are finding the population at time t equals 5 days. So our t is 5. So from this equation, the population at time t equals 5 will be equal to 2 because p naught is 2. Then k is 0.7944 and t is 5. And when you compute this, you get 106.181. And in some textbooks, they will approximate this to 106. But I'm approximating this to 107 because, we are talking about the population here, human beings here, and we don't have 2.1 human beings. So when we have 2.1 human beings or 2.2 human beings, we mostly run it to 3. Alright, as soon as there is something left over, we approximate it to the nearest whole number. Okay. So this approximated to 107. We see 106 in other books. That means for them they use the normal rule for approximation. Okay. Alright. Then question 2. So question 2 says that suppose the population has 39 members at time t equals 8 and 60 members at time t equals 12. What was the population at t equals 0? So what was the initial population p naught? Right. So from this formula, when we linearize it, we had this. Okay, if you could remember. So that's what we are going to use. So at t equals 8, the population was what? 39. So making substitution, we'll have ln 39 will be equal to ln p naught plus 8 times k. Right, and this is equation 1. Then at time t equals 12, the population was 60. So that will give us the equation ln 60 will be equal to ln p naught plus 12k. We call this equation 2. So now we have to solve equation 2 and equation 1 simultaneously to get k, which will help us to get p naught. So we do that by subtracting equation 2 from equation 1. So doing that will give us ln 60 minus ln 39 will be equal to ln p naught minus ln p naught plus 12k minus 8k, and this will go away. So we get ln 60 over 39, because ln 60 minus ln 39 is the same as ln 60 over 39, will be equal to 12k minus 8k is 4k. So k will be equal to ln 60 over 39 all over 4. When you compute this, you are going to get k to be 0.107695729. Then you put k into any of the equations, either equation 1 or equation 2, and that will help you to be able to find p naught. So let's put it into equation 2 here. You can also put it into equation 1, you get the same answer. So we get ln 60 will be equal to ln p naught plus 12k, and now this is k. So making ln p naught the same, you get ln p naught to be equal to ln 60 minus 12k, and this is k. And evaluating what we have here will give you ln p naught to be equal to 2.801995814. So to get p naught, we find the exponent on both sides. So we get p naught to be equal to e 2.801995814, and this will give you, when you evaluate this, you get 16.4775. As I said, some books will approximate this to 16, but because you're talking about human beings here, we approximate this to 17. Okay. Alright, so thank you very much. This is going to be the lesson on the Malthusian model. Okay. So the Malthusian model is used to describe population size, okay, and used to make some predictions. And it was introduced by Thomas Malthus in the year 1798, and it has a lot of applications in several areas, okay, even in finance, in investments, and a whole lot. So thank you very much, and see you in the next lesson.